Hey guys, I wanted to give you some instructions on how to draw a stick structure from a chemical formula. And this can be kind of tricky if you don't have some tips. So I'm just kind of like going to write some things down and give you some hints about how you can um, know how to look at a chemical formula and the order the atoms are in the formula and help you translate that to a structure that you draw. And then a correct Lewis structure. Okay, so I'm going to use two compounds, acetone, which you guys are going to use later this year, and this formula is CH3COCH3 and propanol. Oops, sorry, propanol, not propanol. Propanol, which is an alcohol with 3 carbons. And this one is CH3, CH2, CH2OH. Now, the first thing I want to point out is that I have not written these. There's a couple different ways I could have written this formula. I could have like combined all of the carbons and then like counted up the numbers. So that would have been like C3H6O. In this case, it would be C3H3 578H8O, right? And you can see that the way that I've written these, this is the same thing, right? Like I've just like decondensed, a lot of these in these versions of the way I've written these. Gives me a little bit more of an indication on how those atoms are attached to each other. So as often as we can, Emma and I are going to give you formulas like this, because more than one molecule have these formulas. And so without getting an idea of like how those atoms are attached via a formula like this, there's like more than one way to write that Lewis structure. So if you're looking at something like this formula for acetone here, the way that I've written this is an indication of how those atoms are attached together, okay? So the first thing to know is that carbon can form a total, because it has 4 valence electrons, it can form a total of 4 single bonds, okay? And so carbon is at the backbone of a lot of molecules, meaning that in fats, in hydrocarbons, in fuels, like carbon is a backbone. And then you're hanging, you can think of that as sort of like the hanger. And then you're hanging off that hanger other, what we call in chemistry, functional groups. And functional groups are polyatomic ions, or there's specific things like that we know typically attach in a group to a larger molecule. We call those functional groups. And one functional group that you're familiar with probably is the hydroxide or hydroxyl functional group. And that's when you have an oxygen attached to a hydrogen. And you guys saw that a lot last year in freshman year when you were doing like dehydration synthesis. So you saw a lot of chemical reactions happening at that functional group where you're kind of pulling a hydrogen off maybe and attaching to smaller molecules into like one larger molecule, like for protein synthesis, DNA replication, stuff like that happens. And so the hydroxide functional group is something that you'll see very, very common in chemistry. And so when you see an O and an H written in a formula together, that is an indication that you have a hydroxide functional group, okay? Here, you can see in this part of the molecule here and here, that is a CH3, and that is a functional group called a methyl group. And a methyl group, I'll write this here, is when you have a carbon that is attached to 3 hydrogens and then something else, right? In this case, it's attached to the rest of this molecule, right? This is called a methyl group, right? Okay, and so you can see when I've written that CH3, what's attaching to something else is the carbon, right? And the hydrogens are on the outside. So this is sort of like one of the sort of pieces of the hanger, right? Now, typically what you'll see is that they are attached to other carbons, but what you'll also see is they'll be attached sometimes to other nonmetals like an oxygen or a nitrogen or a sulfur sometimes. But remembering that the carbon can form a maximum of 4 bonds total, or single bonds, or any combination of multiple bonds of that. So let's take a look at acetone first and see if we can intuit some of the ways that this is written. Okay, so I can see that I have a methyl group here, and then if I look down at the other end of this, I can see I have a other methyl group. So I'm going to draw those like this. All right, and then I'm going to put the hydrogens on the outside. I'm going to sort of make that like a mirror image like that. And this is a Lewis structure. I've drawn like a Lewis structure, at least for this segment of the molecule. Okay, now you can see that I have 2 more atoms left. I have a carbon and I have an oxygen. So a couple options here. I can do like a C and an O like that. But another functional group that you'll learn is called a acetyl group, which is a carbon double bonded to an oxygen like this. Okay, now there's really no way of knowing that. You could have easily have put that oxygen in the chain. When you have a carbon and an oxygen and that is like embedded in the hydrocarbon chain, that's called an ether. And so this substance would have had the word ether on it. And since it doesn't here, we are going to make the assumption that carbon oxygen is, that oxygen is off, it's off the chain. Not embedded within the chain. So once you can sort of see that, then you'll know that, oops, I'm still erasing, that oxygen is off of there, like that, bonded to the carbon, but not bonded to 2 carbons, only 1. Now, what you need to figure out beyond that is once you have that skeletal structure is how you need to draw Lewis structure so that you have the right number of electrons or the right number of bonds without maxing out the octet, okay? All right, now, if you had drawn like this, like that, that's still correct. Like if you have, but you would have had to have like figured out that there might be like ways of violating the octet and everything. So it can be a little tricky. And if it doesn't seem super straightforward, it might be that meaning that you're kind of not on the right path to a structure. All right. The next one we're going to do is this propanol. And so I talked about the CH3 methyl group, and I know that I have a hydroxide on the other end that's bonded an O and an H together. And I see that because of that OH is left like a piece that's shown explicitly. Another way you might see a methyl group is to actually, like, if you were looking at that molecule, what atoms come actually first, and you would actually see the hydrogens, like you see here, you actually see a hydrogen before you see a carbon. So you can also see a methyl written H3C and CH3. They mean the same thing. Now I've got a CH2 and a CH2. So that means that I have a carbon and then an H2. But one thing that you can remember is that carbon can form 4 bonds, but hydrogen can only ever form 1 bond. So we never see hydrogen embedded in a chain in a larger molecule. It's never like bonded to more than one thing. It's always sort of hanging off that structure. And because I have a CH2, that means that that carbon is bonded to 2 hydrogens, and then it's going to be bonded to another carbon that it is also bonded to 2 hydrogens. And now that carbon is going to be bonded to an oxygen, which is bonded to a hydrogen. All right. So here's my H3C right here. This is my first CH2. Here's my second CH2, and here's my OH. All right. So this is just a way for you to think about the fact that the way that the substance is written is an indicator of how the atoms are attached together. And so you need to understand how many possible bonds can any element form, and then kind of use those rules to help you determine what's attached to what in the molecule. Okay, so the biggest clue here is that carbon, you know, is going to be sort of at the center, and then other pieces are going to be hanging off of that what we call the carbon backbone. And you're going to learn some like pretty easy, like you're going to start to see, you know, patterns repeated, like OH groups, CH3s, CH2s, you know, are sort of like embedded in the center of a larger molecule. But things like this C double bond O, those are a little bit less straightforward. So if you did the other example where you actually put the oxygen on the inside of that larger chain, that would be correct too, right? So that's all. I kind of wanted to give you some hints about that, and hopefully you'll have a little bit more success drawing Lewis structures for larger molecules.